Welcome back. Today I will be exploring a new example of vector spaces, and that is a collection of functions. Firstly, let's look at what a collection of functions is. So I'm considering a very general case. I'll consider V, that is the set of vectors, to be all functions f of x such that f maps from a to b. So that is, if you want to calculate f of x, you substitute x, that is some value from a, and you get the corresponding value, that is from the set b. Okay, and I'll define the notion of addition and scalar multiplication shortly, but just know that this sort of thing is actually called b raised to a. Alright, I actually want to first of all emphasize how similar this f r to r is to the vectors, that is the real vectors that we saw in the last video. So look at this. Any x bar that is from Rn can be written as x1, x2, xn, but you can also plot it like this. So it won't have values at any real point, it will only have values at certain discrete points, that is at I equal to 1, I equal to 2, I equal to 3, all the way to I equal to n. But notice that the value over here, the components, so to speak, can take any value, any real value, but only the component, this is like a function only, except it can only take values at 1, 2 or 3 or n. Only at certain discrete points it can take values, while the normal function that we are used to dealing with is like r to r. It can take a value at any real number, and obviously and obviously it will spit out another real number as the corresponding output at a particular point. So that's what this is all about. Similarly, even Rn, it's like a function, except it takes values at certain discrete points. But notice that if I want to compare these two, this is basically like a finite list of real numbers, but except each component is indexed by some natural number between 1 to n. In the function, however, it is an infinite list. So it's an infinite list which is indexed by any real number. Alright, so there is no limits over here. Any real number is used to index the values, and f of x in a way is basically the component at index x. That's what this is. Xi is the component at index I, that is some value in between 1 to n, and it's an integer. Over here, this is the x component, and that can take any real value. So this concept applies to any mapping of type A to B actually. So we have established that a real vector, which we have already established as a vector space, and this function real to real, and in fact any function A to B actually is almost the same, just that the indexing set is different. In this case the indexing set is 1 to n. Here the indexing set is the whole real numbers. In this case the indexing set is, well, A. That's what it is. And now I can come to the notion of addition and multiplication. Look at this. Now if f and g are two functions, then this f plus g of x is fx plus gx. That's the addition I have defined. So if you want to find f plus g, and if you want to find the x component of that, you just have to do a component wise addition, right? That's how it worked in vectors. That's how it works in functions. Similarly, the notion of scalar multiplication is also the same. If you want to find the scalar multiplication of a function a f with the scalar a, I won't mention which field we are using over here, but we can use any field as long as you can multiply a and f. Okay, so a times f is basically the component wise multiplication of a with component of f at indexed by x. Alright, so in this case, just look at the similarity between the real vectors and a function. So what I'm trying to say is, I don't exactly need to prove all over again that the set of functions that maps from a to b is a vector space. I don't need to prove that. I've already proven it for real numbers, in which the indexing set was 1, 2, 3 all the way to n. in this case just that the indexing set is a real number, but the underlying core concept is the same. Both of them are like vectors only. uh, so the proofs will be similar, and with that I'll end this video. In the next one I'll actually take a real life example where the application of this concept is there. Okay, so until then, stay tuned and have a nice day.